How far should you look to see the results of nuclear fusion? Out into the universe? Not so far, for results of nuclear fusion are not only in front of you, but inside your body. They're everywhere. The early universe contained hydrogen and some helium, but your surroundings today are mainly composed of heavier elements produced by chains of fusion reactions, beginning with hydrogen isotopes. And elements beyond iron in the periodic table, appreciably more rare, were produced by fusion of heavier elements during supernovae. So all the elements in our bodies, except hydrogen, were likely formed in stars. You've heard it said that we're all made of stardust, a very true statement. Why does fusion in normal stars, those not exploding, not continue beyond the element iron? Let's return to our mass per nucleon versus atomic number graph. We look at the graph as sort of an energy valley. We see hydrogen highest on the left side of the valley. On the right end of the valley is uranium. At the low point in the valley is iron. It's as if nucleons in the light elements wish to lose mass and move toward iron. And nucleons in the heavy elements also wish to lose mass and also move toward iron. In both cases, reactions that move down toward iron release energy. Can you see that iron, positioned at the bottom of the valley, bottoms out? For whether you hypothetically fission iron into smaller parts and move to the left, or fuse it with some other nuclei and move to the right, you'd be going uphill. No energy would be released. Let's think fission for a minute. Suppose a study partner asks how energy is released in both the opposite cases of fusion and fission. What would you say? I hope you'd say it depends upon what is being fused or fissioned. When light nuclei are fused, yum, energy is released. When heavy nuclei are fissioned, more yum, for energy is also released. But in these cases, the reactions are downhill, with decreased mass releasing energy. So, for energy released, decreased mass is the name of the game. But it's not correct to say that nuclear fusion always releases energy. Light elements, yes. Heavier elements, no. And interestingly, I should add, this rule of energy release by way of decreased mass is true of any energy game, chemical or nuclear. The difference is one of scale. A lot for nuclear, tiny for chemical. This explains why fusion cycles in stars cease beyond elements close to iron, where the energy graph slopes upward. Stars are cooled at this stage, big time. Continued fusion ceases. Yum physics. Suppose someone asks you which releases more energy, the fissioning of a uranium nucleus or the fusion of a pair of hydrogen nuclei. Recall that this typical fission reaction produces some 200 million electron volts. That's 200 MeVs. That's a lot of energy per reaction. And the fusion of a pair of hydrogen isotopes produces some 17.6 MeV. So the fissioning of U-235 produces more energy than the fusing of these hydrogen isotopes. The 200 MeV and 17.6 MeV figures are energies per reaction. How about energy per gram of material? Aha! The fusion of hydrogen wins. Why? Because there are more atoms in a gram of hydrogen than in a gram of uranium. Significantly more. So gram for gram, the fusion of hydrogen releases several times as much energy as the fission of uranium. So fusion is commonplace in stars. How about here on Earth? For decades now, nuclear fusion has been a dream source for long-term energy needs. But the outlook for fusion power in the near future is bleak. Various fusion schemes have been tried. The earliest approach, still being pursued, involves confining a hot plasma with a magnetic field. You can see how large this plasma chamber is by the man in the yellow. Other approaches have harnessed high-energy lasers. One scheme is to drop hydrogen pellets into a crossfire of lasers that would ignite pulses of fusion power. The problems, after many years of effort, have been overwhelming. All scenarios have been in a quest for an energy break-even, where energy output at least equals energy input. There was a brief spurt of energy break-even at Livermore Labs in 2013, but sustained break-even has not yet happened. We await a breakthrough where sustained energy output in a device will be greater than the energy input to initiate and sustain fusion. Then we'll have a way to tame power just as the sun and stars do. Hopefully sooner than later. Then fusion will likely be a leading source of energy for generations to come. And humans may synthesize their own elements and produce energy in the process, just as the stars have always done. Stay tuned. I want to leave you with a question. Sometimes pairs of iron nuclei are fused in stellar cores. Does this fusion heat the star or cool it? Until next time, good break-even energy.